Welcome to the third class of Beyond Multivariate Analysis and Introduction to the Forward Encoding Models. During the previous classes, what we were seeing were the theoretical concepts that are behind the forward encoding models. Today, we will continue focusing a little bit more on the practical side of this modeling technique. To do that, we will see some examples of the computations behind forward encoding modeling, and we will also see some MATLAB code applications. The first question is, what is machine learning? Many people think that machine learning involves training some kind of robots to do some tasks and require complex algorithms and mathematical operation. This is not totally true, and if we just focus on the core concept of what machine learning is, and we can understand that machine learning consists of extracting some property of the data and evaluate whether this property of the data is a general thing or is just something that is noise in our data. If you understand what linear regression is and how it works, then that means that you can know machine learning. So we can assume that linear regression is the simplest of the classifiers. In this case, given a distribution of dots, like in this example, that is defined by two independent features, we can try to see if there is a pattern that relates the activity in one and in the other feature. And simply using a linear regression model, we can get the line that is more closely representing the pattern of dots. Once that we are able to fit this linear regression model, the objective will be to sample more data from the same distribution and see whether this weight information that we have fitted with our linear regression is also property in new data sampled from the same distribution. And if we find that this is true, that means that we have learned something from our data, and it's interesting because we can predict new values in the future, and we can also collect data and, on the other hand, predict the labels or recover the labels based on the data. So that will be the same as encoding, and this will be the same as decoding. So in this course, what I have done is to prepare some simple example of linear regression exercises. That way that you can really get familiar with this technique, as is like a light version of the forward encoding models. So what I have prepared for the course is very simple. There will be some artificially generated neurons. That's like 100 neurons, and there will be like 500 artificially generated trials. So everything is simulated. And the logic behind is that the response of each neuron is defined or predetermined by a simple linear regression equation. If X is the stimulus intensity, the weight determines how much the activity of the neuron will be in a linear way. And then we have a noise parameter that it determines how much information we won't be able to explain with our equation. Okay, so what we will do in our exercises most of the time will be to train a linear regression equation here for each neuron, and then we will see whose of these neurons extrapolate the learned weights to a new or the complementary data set, the test data set. Okay, so maybe we can take a look briefly to the MATLAB code. This is like initialization of the random seed to have everybody the same values on our random formulas. And then this is the stimuli that we are creating using a uniform distribution, and it's arbitrarily decided to go from 5 to 1.5. These are the weights or the tuning values of the neuron. So how much each neuron is going to be responsive to the stimulus presented, and there will be some neurons that the tuning will be 0, so that means that they are not responding at all to the stimulus modulations, and there will be another ones that they can have value 1 or 2 on average as responding to the stimulus. So for each neuron, for each one of the 100 neurons, we will have one weight value, and then each neuron will have some variability in each trial. Sometimes the neurons will fire differently depending on the stimulus presented. Then we are also adding some noise, and here we simulate the data. As you can see, for each trial and for each neuron, we are generating some noise data, and then we are generating the activity based on a linear regression equation. The weight here is going to multiply the stimulus here plus noise. Then we will visualize the data. Here we divided the first half of the data to train our simple linear regression classifier. We get the weights, and our first exercise will consist of calculating, based on the weights that we have calculated, you will need to calculate the noise. So this is pretty simple. You just need to pay attention to these equations here, and if you have the data and you have the weights and you have the x, it should be pretty easy for you to get the noise. Okay. Now here I will ask you to regenerate the original data, given that you have the weights, the noise, and the stimuli. So you have all these three ingredients. You can easily regenerate the y values. Okay, so you should get the same values as you had in the beginning, or very, very similar values. And then the next objective will be to test the weights that you have learned from the first half of the data set on the second half of the data set. So you have to use the weights to predict the activity in the second half of the data set based on the x values of the stimulus. And then you can plot it and see which of these neurons have a weight that is 0, which neurons have a weight that is 1, or which neurons have a weight that is 2. So this way you can really see the activity profile of our simulated neuronal landscape. Okay, so that will be the first exercise. Now that we have reviewed a little bit the simple linear regression, we move to something a little bit more complex, multiple linear regression. So multiple linear regression is what is in the end behind of forward encoding modeling, and also behind many other decoding techniques. What is the difference between the multiple linear regression and the simple linear regression? Very simply, the difference is that in simple linear regression, we only have one regressor and a noise parameter or intercept, and then in multiple linear regression we can have an indefinite number of regressors. So formally we can describe a multiple linear regression this way. So we have for each trial one y measurement, and then we have multiple regressors that are in theory explaining activity in each one of these measurements, and these regressors are weighted by one value. And then we have noise, which is all the activity that is not explained by our model. It's also called the error term. So many times what we want to find out is what is the weight of each one of these regressors. If one regressor has weight 0, that means that this regressor is not explaining anything of our data. And if one regressor has a positive value and different from 0, that means that it is positively related with modulations in the activity in the y term. So the stimulus, going from the stimulus to the neural activity, as we said in the previous course, is called encoding. And this is what we are going to do here, to find the underlying mathematical relationship between the activity that we measure and the stimulus that we are presenting. Okay, so in order to test the forward encoding models, we need some data. We can also artificially generate some data, as for example you will find in the orientation or create orientation MATLAB script that I have attached in GitHub. So if you want to play around with your artificially or synthetic data, then you can use that script. But for the case of this course, I wanted to use real data. So I used some data borrowed from Pim Moster, and who is actually the author of this tutorial that I have recommended in the past. So I think that you should read this, and also has created the toolbox that I have modified for this course. So at the same time, I have used data that he originally used to illustrate how to use the forward encoding models. Okay, and this data consists, if I'm not mistaken, in the presentation of different gratings, and these ratings could have one of 8 orientations, and they are presented for 250 milliseconds. Then there is some resting period, and then another stimulus is presented. The data belong to just one participant, and we have 273 MEG channels, okay, that were recorded. The first thing that we have to do, once that we have the data, is to take these stimuli and linearize them. And how do we linearize these stimulus? In this case, it's very easy because they are not naturalistic images and they are almost decomposed in simple features, but we need to pre-create some channels. So imagine that we have trial 1 and it's a 45 degrees grating, and we have trial 2 and it's a 135 degrees grating, and so on. So what we have to do is to take this information and then create X number of channels, of stimulus channels, which are defined in this case by these tuning functions in gray. Okay, here there are like 10. And these tuning functions, each one of them is centered at one orientation value, and they are all having the same spread or width value. Okay, so this width value is determined by the kappa parameter, which is some kind of sigma, but for circular distributions. So if we take the 45 degrees stimuli and we see how much information this stimuli has in all these theoretical channels, as we know that, so these channels are not created in an arbitrary way. We know that in visual cortex, there are some units that are tuned to different orientations. So that's why we have created this. So we want to know how much hypothetically each grating will activate each one of these possible neural populations, okay? So the 45 degrees stimuli will probably activate a lot these two populations that are closely centered around the 45 degrees, and probably won't really excitate too much a population that is tuned to 135 degrees. And the 135 degrees stimuli, we can decompose it in the different channels, and we could predict that it's going to stimulate a lot a 135 channel, but not too much a 0 or 45 degrees channel. So we can formalize this as a regressor variable this way. So for each trial, we divide the orientation in all these predefined channels that corresponds to each one of these gray curves. So once we have this, we have one of the important ingredients that we need for our equation. I'm going to explain with a little bit more of detail how we go from the orientations to the values, okay? Because now I explain here the concept, but I didn't explain how you can get the values. To get the values, what you have to do is to follow a sequence of steps that I will ask you to replicate during the practical session, and is in the design BH function. And what it's doing is, first, we create some predefined channels. We can have as many channels as we want, dividing from 0 degrees to 180 degrees, okay? So in this case, we have 8 channels. So each one of the values in the x-axis is one channel. So this one will be probably 0 degrees. This one will be centered at 20 degrees. This one 40 degrees, okay? And here we have the trials. We have expanded this matrix to have as many rows as trials we have in our dataset, okay? So this is our channels template. We can call it like that. And then we are gonna create something similar, but for the trials. So we have our trials and we have arranged them in order from 0 degrees to 180 degrees presentation. So all the 0 degrees stimuli are here. All the 20 degrees stimuli are here. All the 40 degrees trials stimuli are here, okay? And we have expanded in the columns to have as many columns as predefined channels that we have created. The reason for that is that we are going to convolve these two matrices together. And well, in this case, it's not really a convolution, but it's just a subtraction. So you want to see how much the information in each trial is different from each channel. So if you subtract this from this, then you get this matrix here. And in this matrix here, which indexes the difference between the two, so greenish thing means that they are like very similar, and yellow they say that they are like more different, and blue is also very different. So in the diagonal, we can see that is the greenish. So this is normal because here this is a stimulus that has orientation 0 degrees, and this is the channel of 0 degrees. So there are no differences here. And if we go below to the bottom, then for example here we have the stimuli with 100 degrees, so it's very different from 0 degrees, so it's really yellow, okay? So now that we have the differences, we want to compute the weights. And what can we take as weights? So what we can take is the density, the probability of each difference within the normal distribution center at 0. We are not using a normal distribution in this case because we are in the circular space. We are using degrees, so that means that a 90 degrees orientation is the same as a 270 degrees orientation, or a 0 degrees is the same as a 180 degrees. Okay, so in circular space we can use the von Mises distribution, or we can use the half-wave rectified cosine. So this distribution has a shape like this, and as I said previously, you can define it by the center of the distribution, that in this case is 0, and the kappa, which is the spread or the concentration parameter. 0 means that is completely uniform, so all the orientations are equally likely. See that these are radians and not degrees or longitudinal unit. And 8, for example, is much more concentrated, the information, the probabilities, okay? The most likely degree that you can get is 0. So to transform these to densities, what we do is to use a von Mises distribution with a kappa parameter equal to 5. This is also arbitrarily decided. We can try different values and see how the results change in the end, but we are not aiming to do this in this practice. So now we can pass all these different values through our distribution, and it's centered in 0. So when the values are very different, then we'll get a small probability. But if the overlap between the orientation of the channel and the orientation of the trial is the same, that means that we are exactly in the center, so the probability is very high, okay? So we have to do this for all the channels, and that's how we are linearizing all the stimulus in different weights. Now I have to explain that for our analysis, we are going to simplify this a lot, and we are not going to analyze all the time points of our data collection, and we will focus on the 200 milliseconds. Here you can see the topo, and this is the dipole of the topo, and here I have plotted the ERF, so you can see that this is 0 seconds and when the stimulus is presented, and we have a peak of activity here and another peak here at 200. So this is the part from where we are going to analyze the data, and the data consists of 760 trials and 273 MEG sensors. Then we have our stimuli transformed to regressors after the linearization, and we can start fitting a forward encoding model. We will start fitting the forward encoding model following a multivariate approach. So I think that we can summarize the ways to do this in a multivariate way or in a univariate way. This is a multivariate approach because what we will do is to fit a linear regression model, a multiple linear regression model, using all the different sensor features of the scanner and half of the trials of the data set. And then we will fit this for half of the design matrix. Okay, for this is the channel 1, let's say 0 degrees. So this is the X and this is the Y, so we can fit one model and get the weights for this channel. Then we can do it, we can get the weights using this equation, and because it's matrices, it's something like this. You don't need to care too much about this because the code is already there for you. Then we will do it for the second channel, again, the data as a function of the second channel, and we will continue consecutively doing the same for the remaining channels until we go to the end. So then we will have the weights for each one of the channels that we can like concatenate all together, and that will be our weight matrix. The next thing that we have to do after we generate all this weight matrix is to test an encoding model if it's actually predicting the information. If you go inside of the code of the forward encoding model, you will see that the neural activity data, the Y data, are the mean. You might be wondering if it's necessary to demean the data or not. The thing is that it depends. The meaning basically consists, if you have two clouds of dots, that in this case, as you can see, they could be decodable by a classifier. They can be separated along this axis, for example, very easily. So if you demean them, you are simply moving this cloud of dots and centering around 0, okay? So if your objective is to classify one condition versus the other, demeaning the data wouldn't make any difference, okay? Because the relative distance between the two variables is still the same when you are in a non-demean space or in a demean space. But if you are fitting a forward encoding model for each condition individually, then it's very important what is the distance with respect to a center point. So in forward encoding models, you need to demean the data before you train your model and before you test your model, okay? But if you are just classifying between classes, you wouldn't actually need to do it. It wouldn't make a big difference. So now that we fitted our model and we have discussed the thing about demeaning or not demeaning, then we move to the next step. Let's try to predict some data, and this will be another exercise that you will have in the MATLAB practical session. So once we have the weights and we have the STEAM channels for the second part of the experiment, okay, then we have to use this, let's say multiply these X values by these weight values as is in this equation, right? That we have extracted these weight values, we extracted from the first part of the experiment, okay? But now we are gonna see if we can, using these weights and using the X values on the second part of the experiment, predict the Y activity. And then we predict the activity and we compare it with the actual data, with the second part of the data. If the prediction is good, that means that our model is working and there is information that we are modeling. And this is a forward encoding modeling. We are predicting the activity. And also, we can use the fitted model to decode the stimulus. So in this case, okay, this is the normal equation. And if we want to decode the X, okay, the stimulus, then what we have to do is to move the Y term to the other side. Because we are working with matrices, if we want to do this, we have to apply this operation. So it's the weight matrix divided by the weight matrix and multiply by the inverse of the transpose of the weight matrix and multiply by the data. Okay, so now we have our data weights here, and we multiply it with the actual data, which is what we do sometimes with classification, and then this is going to give us some predictions for the activity in the channels of the second half of the experiment. So again, what we can do is to verify if the activity that our model is giving us for the stimulus channels, okay, the regressors, is the same as the one that we can calculate from the second part of the experiment. If this happens, that means that we can decode information. And actually, if we apply some operations that you don't need to understand, you can like decode the specific orientation of each trial. Good. And now I'm gonna very briefly describe what is the univariate approach. So fitting the forward encoding model is kind of the same as fitting a multivariate, fitting in a multivariate way, but with the difference that now we take the data set and we are like taking the first sensor, the first MEG sensor, and we model it as a function of all the channels that we have here. So this is like the same as when we are like fitting a GLM in fMRI, that you have one voxel and then you have your regressors for each stimuli in all your trials, and then you try to predict the activity of that voxel as a function of all these regressors. And then you can do this for all the sensors one by one, and then you can get some data weights. So you will do something like this, and this is what you will get in the end. And using this technique, you can use it to predict again the same data set, or you can use it to recover the stimuli, as we did with the multivariate approach. So it's conceptually the same, but the only thing that is changing is that now instead of like introducing the whole array of data, we are just going sensor by sensor. Okay, so in the end, what you should get is, if you run the multivariate approach with the encoding model, if you try to predict activity, so this is the correlation between the actual activity in the second half of the experiment and the real and the predicted activity in the second half of the experiment. And these are the correlation values for each one of the sensors of the MEG channels. And you can see that the model is predicting the activity mostly in the occipital cortex, which makes sense because it's the area that represents this information. So we are like more or less being able to know from where the activity that we are decoding is being derived. Then the cool thing is that we can recompose the stimulus channels based on the activity in the second part of the stimulus and the ways that we calculate it. And for example, a 0 degrees stimuli has a strong weight at the 0 degrees, and it goes down for other orientations. And for example, the 54 is also growing around this point. And in the end, if we are like collapsing all these tuning functions and shifting them to be centered at 0, so it's like we push them to be all on top of their central value, we can see that the tuning is quite accurate in the end, right? So we can recover the tuning. So that means that imagine that you have an experiment and you have one localizer and 3 different conditions. So you can use the localizer to train and recover the different channels, and then you can see how this tuning function changes as a function of your experimental manipulation. So then you can see how the information is transformed. And here you can see the output of the decoding. So what are for each trial, what is the predicted orientation? So this is the real values of the stimuli, and these are the predicted values in orientation degrees. And more or less we can see that the correlation is above 0.24. And so here it's 180, but remember that this is circular, so 180 is more or less the same as 0. Now, if we go to the univariate approach, what we can see is that using the coding approach, we can predict very well the activity at the sensor level. If in fact, we can predict even better the activity here for each sensor. I think the pattern is cleaner than here, okay? So it's overlapping the pattern, but here the correlation is higher and there are no so much negative values. But on the other hand, it seems that we are losing some information about the weights for each channel. Okay, so recovering the channel information is being a little bit suboptimal. Nevertheless, the accuracy on decoding the particular information, so if we use, although here we don't see the shape of the channels, if we use these channels to predict the orientations and recover the orientations, we can see here that is working as good as in this other case. So it depends on what type of information you want to highlight. Maybe it's better for you to use a multivariate approach, or maybe it's better for you to use a univariate approach. Use these images as some kind of copy of what you should expect from your analysis, okay? Finally, this is some bibliography that you can read where they have used very similar techniques, and actually in these two papers they have used the approach that I'm showing in this class. I'm gonna show you a little bit how is the script for the practical session, the orientation decoding and forward encoding models. Here it is. So you should load the test data orientation, then we give them some format. We have the time dimension, the labels of the MEG sensor, and then we have to transform these values to degrees, because now the labels are 1, 2, 3, 4, so we have to transform them to degrees. And here I just like put them inside of a time block structure of field trip, so you can plot it and you can visualize the raw data. Then this is the transformation for the decoding. This is taking the time point of interest. Here we are like using a split half decoding approach, so we are like dividing the data in a test train or train test manifolds. So we get the indexes, and then here is the linearization. We define how many channels we want, and here the first exercise will consist of going inside and generate a plot with all the labels and showing what it is being plotted in each one of the what is each transformation the orientation are suffering until you get the design matrix. Okay, so I'm not asking you to use too many mathematics. What I want you to do is to understand how the things are working, at least in a conceptual way. Then you can visualize the design model, and then you can also place the appropriate labels for each one of the things that you are plotting. Okay, and here what you have to do is to decide. So here what you have to do is to go inside of the try multivariate encoding function, see how it works, and decide what ingredients you need to feed to this function in order to give you the decoder output. Don't worry about the regularization parameter. The regularization parameter is one value that is used when it happens very often that when you don't have too many data and you feed a multiple linear regression, it can happen that variability of your data and noise produce some strange or weight values. So with the regularization parameter, what you do is to squeeze a little bit your distribution of weights to not deviate too much from what is expected to happen. Okay. Yeah. I believe that the remaining code is easy to follow, just reading the different instructions that I have attached. and the functions are self-explanatory, and also I think that you can follow them very easily if you go inside and try to debug how they work. In general, I think that this is the end of this part of the course. Hopefully this has been useful for you, and I wait to see you in the practical session where we could talk online and solve any doubt that you can have. Thank you very much for your attention. Goodbye.